Today's problem is Leetcode 712. Minimum ASCII delete sum for two strings. You are given two strings, S1 and S2. Your task is to delete some characters from either string so that both strings become exactly the same. But there's a catch. Every character has an ASCII value, and when you delete a character, you pay a cost equal to its ASCII value. The goal is to make the two strings equal with the minimum total ASCII deletion cost. You are allowed to delete characters from either string, in any order. You are not allowed to rearrange characters, only deletions are permitted. Finally, return the minimum ASCII sum of deleted characters required to make both strings equal. Example 1. Input. S1 equals C. S2 equals EAT. Step 1. Understand the goal. We want to delete characters from both strings so that the final strings are exactly the same. The total ASCII value of deleted characters is minimized. Step 2. Compare both strings. S1 equals SEA. S2 equals EAT. The common subsequence between both strings is EA. So the best plan is to keep E and A in both strings and delete the rest. Step 3. Delete extra characters. From C, delete S. ASCII value of S equals 115. From E, delete T. ASCII value of T equals 116. Step 4. Calculate total cost 115, S, plus 116, T, equals 231. Final result output equals 231. This is the minimum possible deletion cost. Example 2. Input. S1 equals delete. S2 equals leet. Step 1. Find the best common string. We try to convert both strings into the same string with minimum deletion cost. One optimal common string is let. Step 2. Deletions from delete. Original. DELETE. To get let, delete. D, ASCII 100. E, ASCII 101. E, ASCII 101. Total deletion cost from delete. 100 plus 101 plus 101 is equal to 302. Step 3. Deletions from leet. Original. LEET. To get let, delete. E, ASCII 101. Step 4. Total cost 302 plus 101 is equal to 403. Why not other options? Converting both strings to LE cost 433. Converting both strings to EAT cost 417. Both are higher than 403, so let is optimal. Final result output equals 403. Key takeaway. This problem is about keeping the most valuable common characters and deleting the rest with the lowest ASCII cost. Intuition. Instead of directly thinking about what to delete, we flip the perspective and think about what to keep. If we keep a common subsequence, we don't pay the ASCII cost for those characters. So the strategy becomes: keep the common subsequence with the maximum total ASCII value, and delete everything else. Key observation. If sum, S1, equals total ASCII value of first string, sum, S2, equals total ASCII value of second string, common sum equals maximum ASCII sum of a common subsequence, then minimum delete cost equals sum, S1, plus sum, S2, 2 times common sum. Why multiply by 2? Because those kept characters appear in both strings. DP explanation, based on this code. DP definition common ASCII sum DP, I, J, equals maximum ASCII sum of a common subsequence between first string, 0, I, and second string, 0, J. DP transitions. Case 1. Characters match first string, I, equals second string, J. We keep this character. DP, I plus 1, J plus 1, equals DP, I, J, plus ASCII, character. Case 2. Characters don't match. We skip one character and take the better result. DP, I plus 1, J plus 1, equals max. DP, I, J plus 1, hash skip char from first string. DP, I plus 1, J, hash skip char from second string. This is exactly the same structure as LCS. But instead of length, we maximize ASCII value. Example walkthrough, C vs EAT. S1 equals SEA. S2 equals EAT. Common subsequence equals EA. ASCII sum equals 101 plus 97 is equal to 198. Total ASCII. C equals 115 plus 101 plus 97 is equal to 313. EAT equals 101 plus 97 plus 116 is equal to 314. Total equals 627. Minimum delete sum. 627, 2 times 198 is equal to 231. Matches expected output. This problem is a variation of LCS. Instead of maximizing the length of the common subsequence, we maximize the ASCII sum of the common subsequence. The minimum delete cost is simply the total ASCII sum of both strings, minus twice the ASCII sum of the common subsequence. Why this solution is excellent? Number 1. Clean. Number 2. LCS-based, easy to explain in interviews. Number 3. No tricky edge cases. Number 4. Intuitive formula at the end. Alright, we've finished building our dynamic programming solution. We're using a DP table to store the maximum ASCII sum of a common subsequence. Now let's run the code with the sample test cases and see if our logic works as expected. Nice. All test cases are passing successfully. Our DP logic correctly finds the maximum ASCII value we can keep, and then calculates the minimum delete sum from both strings. No edge cases missed, no extra conditions needed, clean and efficient solution. Boom. Accepted on the first submit. That's exactly what we want to see. So that's how we solve minimum ASCII delete sum for 2 strings. Instead of directly thinking about deletions, we focused on keeping the most valuable common subsequence using dynamic programming. This LCS-style approach makes the problem simple, elegant, and interview-ready. If this explanation helped you, don't forget to like the video, subscribe for more clean Leetcode explanations, and drop a comment if you want a space-optimized version or more DP problems. Thanks for watching. I'll see you in the next one.